So yesterday, or not yesterday, a week ago, I argued why it's worthwhile looking at structured models, and we started talking about undirected graphical models in a qualitative fashion. And today I want to give you more insight on what these priors look like, how they act, and how they can be well, put to good use in computer vision. There is no single book covering the entire lecture series, but actually this one by Simon Prince goes a long way. So there's none of the neural network stuff in there, but much of the rest. And I brought it, you can look at it in the brick. And the other book is one of the best for today's topic. So what we will treat in 90 minutes, you can follow up in more detail on 400 pages or so. Yeah? But don't tell me I didn't give you a reference. Okay. I brought today as a motivating example this one. This will be familiar from the exercise that you've seen. We here have an OCT scan, optical coherence tomography scan of a retina. And let's say that we want to segment this into the individual layers. And an expert has annotated these layers here. Now we can use some classifier to look at a local patch in the image and try and decide what it is. And how successful this classifier will be depends on how much context it sees. So if the classifier sees, let's say, a patch this size, then it might confuse this class with that class, which, if we look at it, through a keyhole this big, looks pretty much the same. Similarly, this class here probably looks quite similar to that one here. Now you can obviously try and work, with larger patches and hope that whatever features you can extract from there will help you obtain a better local decision. And that is true indeed. But in all applications, you eventually come to the point when such local decisions make mistakes. And then the question is, what kind of constraints or what kind of priors can we use to still obtain the correct solution? So let's use that as an example, and let me put down again the important formula that we saw last time. So we're looking at the posterior of some latent variable that we want to estimate, z, given some input or some observation x. And according to Bayes' theorem, we can rewrite it as follows, where this would be the prior, that would be the posterior, and the thing at the bottom is really expensive to evaluate, so we usually try and avoid this whenever we can in computer vision. And so whatever a local classifier can tell us, did I write posterior here? Why is nobody complaining? Likelihood. Thank you. This is the posterior. Thank you. So, whatever a local classifier can tell us, we will, in this context here, interpret it as likelihood. And we're going to cheat a little bit, because usually the kind of classifiers that you use here, like the random forest that you saw in the exercise, this is actually a discriminative classifier. It doesn't know anything about probabilities. It never was designed to deliver a likelihood. We're just abusing it as a likelihood term here. And if you use a random forest or a support vector machine or a neural network, These are all different ways of obtaining a local decision, and whichever of these means you use, you can insert it in this formula. And this is why today I want to focus more on the prior. Let's speculate again for a moment, what a good prior could look like. So let's assume that we have a local classifier, and let's assume that it mixes up these two classes that we've seen. So it's correct some of the time, but it also makes mistakes sometimes. And I would like to know, so Z is a label image, P of Z is the probability of a whole image full of labels. And what would you argue, what set of labels should have or what configurations of labels should get a high prior probability, and what configuration of labels should get a low prior probability? Okay, so let's use words here. I would actually like to discern more layers than have been indexed here. So I'm going to call this class here A, and this class B, and this one C, and this one D, and this one E. So what should a good prior tell us about a distribution of labels across pixels for these different classes? Yeah, go ahead.
There's some high probability that at the y-axis we have an increasing number of the layers, and at the x-axis we have probably the same layer. These same labels.
Yep. So horizontally, we have a great bias of having the same layer, a label, and vertically, well, also because these layers have some width, but we occasionally allow for transitions, yes. Can you say something more? Because we have this predefined order, it's always A, B, C, D, E. It's always the same sequence.
If there is a layer missing, it's probably not the right label.
So you're saying, let's say C is not allowed to touch E, for example, yeah, except maybe, possibly there. But in general, so C next to C would be okay, C next to D would be okay-ish, and C next to E would be forbidden, and C next to F would be forbidden, and so on. So that's the kind of prior knowledge that we would like to instill in our computer vision method here. Okay. So we want an expression for the prior, which on the one hand is easy to formulate, which doesn't have too many parameters, and which ideally is computationally tractable. And yet we wanted to say something useful about the image. And I've here shown you samples from two different priors. So on the top, we have two samples from a prior that I've called A. And at the bottom, we have two samples from some prior called B. And here we have a gray coding of different classes. So let's say white is class A. Before I use small letters, let's say white is A. And then this bright gray here is B, and the dark gray is C, and the black one, let's say this is D. So here in an example with just 4 classes, there are different priors. Yeah? 2 samples from prior A, 2 samples from prior B. Which do you think would be a better prior? Or anyone thinks prior A would be better for natural image? Nobody. Okay, good. We agree on that. Now, on the other hand, if we look at these samples here, you know, they don't look much like natural images. They don't look like retinal images. They don't look like semantic segmentation of pedestrian, car, street. They are, you know, fairly primitive blob priors. Yeah? They say it's better. This prior here apparently told us it's better to have the same two labels of the same class next to each other rather than two labels of a different class. That's all the prior says. And this, what we see here in the bottom, is the prior's expectation of what our world looks like. It's pretty primitive, right? But it's better than the one above. Yeah? So the one above simply says, well, it's no prior at all. Right? It just says there's no prior expectation about how classes are distributed from one pixel to the next. And this prior here tells us it is better to have two labels of the same class next to each other. I try to say here in the land of the blind, the one-eyed man is king. Yeah? So it's still poor, but it's much better than not doing anything. Yeah? And for the OCT example specifically, we could further strengthen the prior or make it more strict, as we just discussed, by really disallowing or charging a very high penalty if two classes are neighbors which should not be neighbors. Okay, question, yeah?
Yes, I not really get the connection between those images and the priors, because we said for now that the prior only has information about the neighborhood of lens, but in this picture, does this imply there's even an assumption on the how big a certain area is?
No, this prior makes no assumption about how big a certain area is. Yeah. What it does do, however, because it penalizes label transitions, is it does not like boundaries. And if we want to maximize the area to boundary ratio, then it's good to have few large blobs. Yeah? So small blobs here are implicitly penalized. Yeah? Go ahead.
What exactly do you mean by a sample of prior?
Okay.
What do you mean by prior? So, I mean, I do get the idea that we have some structure in mind and we want to penalize some transition, but is a prior a function? Is it just a value P of that?
A prior is a distribution, yeah. So you know, the distribution, if you discuss distribution, is always the Gaussian. And if I draw samples from this Gaussian distribution, you know, I just use my random number generator and I get a couple of samples. Yeah? So that's what I would indicate here. We have a distribution over images, so each sample is a full image. Thanks for clarifying. More questions? And the prior lives in an extremely high dimensional space, yeah, because we have, in this case, 4 possible classes per pixel, and then, I don't know, 1 million or something pixels. So here it's a discrete prior, or a prior over discrete space, but it's, you know, very, very big. Yes?
What are the x and y axes in these samples? So it's just the position, and the label is randomly sampled from this prior distribution, depending on the neighborhood already, or how? What does the picture exactly mean?
Okay, so here the axes are just the spatial axis of a picture, and so the prior that was used here actually looks like this. So if we have the classes A, B, C, D, E, there is 0 penalty if A is a neighbor of A, and then there is a constant penalty, let me write C, everywhere else, if one class is next to the other. So that's different from our retina example, for example, because here we do allow E to be a neighbor of A, or so A and E being neighbors here is no more expensive than A and B being neighbors. And in our OCT example, we would do that differently. But this is the energy function, which if so this is used to define the energy between two adjacent sites. So if I have, let's say this is for pixel Zi, and this is for pixel Cj, and the table that I've plotted here is the energy that depends on Zi and Cj for I being a neighbor of J. Yeah? So for I a neighbor of J. And then we can sum these energies over all pairs of pixels, and we get out a global energy of all labels. And the link to a distribution is that this energy, or this Gibbs measure, I can take it as argument here in an exponential for a temperature of 1. And this is the same as the probability of Z if I normalize it properly. So capital Z here, oh, that's maybe not a good letter. Let me write capital, or I'm writing it out, the partition function. Yeah, so I need to normalize this thing properly, and then it gives me the probability for a given configuration. So this is the probability distribution, just like the Gaussian one that I showed further up. And here we see samples from this probability distribution. And I want to show you how you can generate such samples. I've here used a program called Ants in Fields, which was developed by a member of the Winkler Lab by Rainer Friedrich, and it comes as an accompaniment on the book. And so the interaction strength parameter, these people don't call it C, but they call it beta. So in this case, beta was set to 0.8. I have 4 classes. I can initialize the thing randomly, and I can then run a Markov chain under this distribution. And I will show you later how to so what's the pseudocode of doing this? But this is how I generated the samples that you saw. And if we let this run for long enough, then it tries to sample very highly probable states, and the very highly probable state, according to this prior, is just a uniform distribution, just a single class. Okay, but more on that later. So for now, I would like to say in more abstract terms, what is an undirected probabilistic graphical model? And I'm going to abbreviate it UGM for short. It means that I formulate some distribution, as a function that factorizes in a simple way over the constituent random variables. So these undirected graphical models, they also have another name. They're also called Markov random fields. Or MRF for short. And they are somewhere at the interface of, so I'm going to show you a Mickey Mouse plot graph theory, which allows us to study independence relations in Markov random fields. It's a big topic in statistics and machine learning. And if we want to use it, we need combinatorial optimization for discrete MRFs or continuous optimization for the others. And here in the center of this world live Markov random fields. So I want to tell you how these are characterized in general. A Markov random field is a countable set of random variables that are endowed with local interactions, and it is most interesting if these interactions are sparse. So if each random variable interacts only with a few others. And to specify now a specific member of this family, we need to say precisely, on the one hand, what is our set of random variables? In the OCT example, in our OCT retina example, we would have one random variable per pixel. Yeah, that's the state that we want to model. What class does each pixel belong to? But there are many more choices. Yeah, so in other applications, people use, for example, one random variable per superpixel, or they use one random variable per detection of an object, or you can use one random variable per tracklet in a tracking application, and so on. Yeah? So there's a great modeling freedom here depending on what specific problem you're trying to solve. So here you say how fine-grained you want to treat your problem. And by associating one random variable per pixel, on the one hand, we make life easy for ourselves because our pixels live on a Cartesian lattice, so it's a fairly primitive structure. On the other hand, we incur, when we have 1 million pixels, we have 1 million random variables. So depending on how precisely we set up the problem, that will be expensive to deal with. Okay. Next, we need to specify the set of interactions. And this is a very important choice. These interactions we can specify by saying what factors we want to use. I'll explain in a minute what factors are and their scope. So this is about, which random variable sees which of its neighbors, essentially. And these interactions can be expressed as a bipartite graph. Write this more nicely. Bipartite graph. For those who have not heard about bipartite graphs before, those are just graphs with two kinds of nodes. So in our case, we have one set of nodes for the random variables and one set of nodes for the factors to tell us which random variables together enter the expression when I factorize my global distribution. So I'm going to show you a canonical picture. That is drawn whenever we talk about random variables on a lattice. Because we're lazy, we typically just show, okay, let me use more colors here. Let this be the random variables here, and I'm going to label them explicitly. So this is Z1, Z2, Z3, Z4 in an image with 4 pixels. Usually I have 1,000,000 of them. And now if we look at our expression again, we can somehow encode this expression here in the Bayes theorem. We can encode it in this plot. So I will say P of Z given X and I now need a factor for this P of Z. And if I make no simplifying assumptions, then I would just say my prior probability is a function of all random variables. And then I also need a term for these likelihoods. These are also factors, and I could now either say, so again, without simplifying assumptions, I would have another factor here connected to all random variables. But this would be a very difficult model to deal with. Yeah? So we try and make things simpler. Yeah? So I can make a first simplification, and I can say I factorize my likelihood. So I say P of X given Z is simply a product here over all pixels. And if I try and draw the corresponding plot,
this factor means multiplication?
Factor means multiplication. Yeah. So factorize likelihood means I want to write it as a multiplication of several terms. When I factorize the likelihood, I can, for example, plot it like this. And if I just write P of x given z, this is a completely general expression. And by now saying that the likelihood of each pixel's observation only depends on the random variable of that observation, that's a huge simplification. But that would still leave me with my complex global prior here. So the next thing I can do is try and make my prior simpler. I can do another simplification. I can say I want to factorize my prior. And now it's up to me how I want to do that. But something that we've been discussing is to just introduce interactions between the neighbors. So I would have one interaction between these two neighbors, one interaction between those two neighbors, and so on. So to color code, what I have here, my z's were purple. And by writing this as a product, I just, in terms of the graph, I just say that these factors, they act on the same set of random variables. They act on the same graph. And in this graphical way of summarizing my model, I will endow each factor with edges that connect it to its argument. Okay, and you can see that I have respected the pattern of bipartite graph by using squares for the factors. So in this kind of picture, this is also called a factor graph notation that I've used here. I've used squares for the factors, and I've used circles for the random variables. And you see that, at least if I draw this cleanly, you see that random variables are always only connected to factors, but not to other random variables, and vice versa. Factors are only connected to random variables, but not to other factors. Okay. So in my formula, where are the observations? I have omitted the observations because they are fixed. I could have added them to the picture if I like. But my observations are not free anymore. I have made these observations, so they are fixed. And this is often indicated by shading. So shaded circles are observed or fixed random variables. So why this whole business about graphs? Because from these graphs, I can read off interesting properties. I can code the locality of the interactions, and I can see which variables are conditionally independent of which others. So what I can see here is that each graph specifies not a particular member, but a whole family of probability distributions. Namely, all probability distributions that fulfill the same conditional independence relations. And what I can code for in such a graph is that the probability of some random variable Zi given, let me write a capital letter here to stress that it's a random variable, given its neighbors and given all the rest. So it's all Z except the neighborhood of I and except I itself. This is the same as the probability of Zi given only its neighbors. Yeah, so if I want to look at the state, let's say, or the conditional probability of this random variable given all others, if I'm interested in this particular random variable given the states of all others, the only thing that matters are the variables that are connected in the factor graph with factors to this variable of interest. So in this case, its horizontal and its vertical neighbor matter, but the diagonal neighbor does not matter because it's not connected via a factor. And well, if I'm only connected to 2 out of 3 pixels, that's not very interesting. But if I'm connected only to 2 out of 1,000,000 pixels, that makes for huge savings in complexity and then also in computational complexity.
Excuse me. Orientation on the left side, the bars.
These things here, I just meant to say without. I tried some set notation. Yeah, I tried to say all variables except the neighbors of I and except I itself. So by just looking at the factor graph, I can already see what kind of or what order of interactions a specific model encodes. And this gives me important information about the mathematical structure of the optimization problem. For example, if my graph is just a tree, then I know that I can always find the exact, then I know that I can find the mode of my distribution in polynomial time. Whereas if the graph has loops, like this one, then it is in general an NP-hard problem, except in certain special cases that I will enumerate a week from now. So this is why these kinds of plots are a convenient language to summarize the structure of a model or the structure of an assumption. Now, to specify a specific MRF, we need two more ingredients, which we can only discuss after the break. But I want to give you a chance to ask any questions that you have right now.
In the graph, why the likelihood above the random variable?
Oh, why did I plot the blue boxes above and not below?
Yes.
It's a completely arbitrary decision. Just to make the plot less, less dense. So the only thing that matters here is the topology of the graph, not if I plot them above or below or anything else. Okay. So I can draw, an equivalent graph would be this one. Whatever. So the layout here is artistic freedom. Only with 4 pixels, I can make a picture like this, and with 1 million pixels, well, I never draw them, but it's more convenient to think about it in terms of what I showed on the left-hand side. More questions? Yeah.
Just a bit more about how the observations came to this side. Really understand much.
Okay. What's the role of the observations in there? Yeah. So I said that we, in real life, so if I had no observations, or just from the modeling standpoint, I could have a generative model from which I can sample both observations and latent variables. In our case, observations are given, and I've been simplifying a little bit by connecting here these likelihood terms, each one to just a single pixel. That is not quite the correct thing to do, because if I use something like the random forest, which is based on filter outputs, then this local estimation of what is going on in a pixel is not just based on a single pixel observation, but on several. So your observation is correct. So I could, for example, make, to be more honest here, I could make more connections. However, because the observations are fixed anyway, what my blue factors encode, or how they can be represented, is just in terms of so-called conditional probability tables. So a conditional probability table. CPT for short. In our case is a vector. If I have 4 classes, it's a vector with 4 entries, and it tells me, for example, what does my random forest think? How likely is it to have class A, B, C, or D at the given pixel without taking into account interactions with neighbors and so on? So I might, I'm making up some numbers, maybe have a 0.7 here, and a 0.1 there, and a 0.05 there, and a 0.15. Does that add up? No. 0.25 there. No. 1.5. 0.15. Yeah. Okay, that adds up to 1. For example, these are the numbers that I get from my random forest, and in terms of my Markov random field modeling, I'm treating them as a black box. So it's not really important to me if I have more connections up there between blue boxes and other observed random variables. You see, a random variable being observed means that I don't need to take it into account for my modeling here. The only thing that matters is the conditional probability table. And the conditional probability table will, of course, look different for each of the pixels because the random forest has seen different observations for each of the pixels. More questions? Okay, so I'm afraid that I have not come to the point where you can ask good questions. Yeah, go ahead.
The green boxes, this is, are the interactions between the pixels, are what we try to do with the little tables to create.
Yes.
So we make them ourselves.
Yes, the green boxes here in this picture encode the kind of interaction that we have been discussing here. And this we either invent it ourselves or we try and learn the numbers in there from data. Yeah? So
if you want to learn these numbers by data, you have images that are fully annotated by somebody, and then you ask how likely is pixel 1.1 to belong to class A in order to get the prior to make this picture.
Yes. So
or we have some other method.
So I have to make some modeling decisions. For example, I have to make the decision: do I want to use a single parameter beta here for all interactions between different classes, or do I want to have different parameters? Yeah? So I could have, for the first off diagonal, I could have one parameter, let's say beta 1, and for the second off diagonal, I could have another parameter, beta 2, and so on. So I have to make this modeling decision, but once the decision is made, when I do structured learning, I use the whole model, so the likelihood with a prior. I do inference on it, so I find the most plausible posterior solution, the maximum or posteriori solution. I come up with a best effort prediction, and I compare this best effort prediction with the ground truth. And it will usually not be perfect. And then the question is, how do I need to change my parameters in order to make it better? And there are a few ways. The simplest way to do this intellectually is to just solve the problem again and again for different values of beta 1. but the problem is when you have many parameters, yeah, so beta 1, beta 2, beta 3, and then you already have to try out a whole volume of parameters. So there are other methods where rather than doing these brute force searches through parameter space, you can try and obtain a gradient on how you should change your parameters for your prediction to become better. But this is what learning is about. And also historically, first people would just invent a model and invent parameters, and then 10, 20 years later came the learning of those parameters. And this is, of course, what we're more interested in here for the lecture, how to learn them properly. Okay, but your first question was, yes, the thing that we draw here, that was encoded in the green box in the other plot. Okay, let's have a break, and then I will go on telling you, how these graphs factorize, what else we need to specify, a graphical model. I will also tell you how to sample from the posterior, and then hopefully you're in a better position to ask more questions.